Hello everyone and welcome to lecture 11 of computer architecture. Today we're going to talk about finite state machines. So a quick review of what we covered last time. Last time we covered memory and specifically looked at two types of memory, SRAM and DRAM. And we're kind of approaching the last part of, we have around a week left in part one of the course. So we recall that memory is a logic block that stores data, and we can either provide an address and read data or provide an address and write data to that address. And we said that there are different types of memory. We had already seen registered files as one type of memory. And then last time we also looked at static random access memory as another type of memory that has higher capacity than register files. But that higher capacity came at a trade-off. It came at a cost. And that cost was that they were slower to access than register files. And also, we were only able to read or write during a clock cycle. We could not do both. Whereas in a register file, we were able to read two registers and write one register on a clock cycle, and we can even read and write to the same register on the same clock cycle. So we looked at how to implement SRAM, and the key differences between implementing SRAM and register files were first that we used latches instead of flip-flops to store one-bit storage elements, and this is what enabled us to be able to store data using less hardware in SRAM. But because we're using latches instead of flip-flops, we were not able to read and write on the same cycle because the latch will update as long as the clock is 1, not just on the active edge. And then secondly, we used three-state buffers connected to one bit line in order for us to do the selection because SRAMs were much larger, and that meant that it was infeasible to build a multiplexer of that size. And that's why we used three-state buffers in order for us to implement the multiplexing. This is a diagram of how we implemented the SRAM. We had rows of latches, and then we had a decoder that took the address we wanted to read or write from. If we're reading, the decoder would enable the state buffer, the three-state buffers for the corresponding row. So if we're reading from row 1, the three-state buffers for the latches of row 1 will be enabled, and that way we will read the values stored at row 1. All the other three-state buffers will be disabled. And if we're writing, then the decoder is going to enable the AND gate that corresponds to the row that we want to write to, and all the other AND gates will be 0, so they will not be written. And for that row that we want to write to, obviously the write signal has to be 1. The clock will pass, and it will enable that the data coming in gets written to the row that we want to write to. So this is how we implemented SRAM. We then looked at dynamic random access memory, and we said that dynamic random access memory also we can either read or write on the same cycle, but it has even higher capacity than SRAM. We can store even more data with the same cost compared to SRAM. But of course, the trade-off here is that it is even slower than SRAM. And another thing, which is where it gets its name from, dynamic. It's dynamic in the sense that the data that's stored in DRAM fades away with time, and we constantly need to refresh it to make sure that we don't lose that data. We looked at the differences between implementing SRAM and DRAM. We said that with SRAM we use latches, and to implement a latch we need a few transistors. We need a bunch of transistors to implement a latch, whereas with DRAM, to store data we just use a single capacitor. And because a capacitor is going to be much cheaper than a bunch of transistors, this is what makes DRAM have higher density, and it enables us to be able to store more data in the same area. However, the disadvantage of capacitors are, first of all, when we read data, we discharge the capacitor, which means we destroy the value that's stored in the capacitor. So every time we read, we're destroying the value that we read, and what that means is that we have to actually write back to the capacitor. So every time we read, we need to actually write back the value that we read. And because of that, reads are slower, because every read is both a read and a write. And then secondly, the other disadvantage of DRAM is that these capacitors leak, which means that even if I don't read from the capacitor, with time, the charge that's stored in this capacitor leaks. And because it leaks, this is what causes DRAM, the values to fade away. This is why DRAM is dynamic. And because of that, what we need to do is we need to periodically refresh the data. So even if we never read this data over here, to avoid losing it due to leakage, we need to periodically read it and write it back just so that it maintains its value. And typically DRAM spends 1 to 2% of the time just doing these refresh operations where it reads and writes back to make sure the value doesn't fade away. And this is another one of the disadvantages, is that these refresh operations, they interfere with the normal read and write operations, and they make access to DRAM slower. So that was a quick overview of what we covered last time. Any questions about last time's material before we move on to talking about finite state machines today? Does anyone have any questions? Okay, all right. Then let's get started. So today we're going to talk about finite state machines. And a finite state machine is a logic block that has inputs, outputs, and it also has an internal state. So inside the finite state machine, there's a state that is stored. And the finite state machine has two functions internally. One of these is the output function, and the output function computes the output of the finite state machine based on the state stored inside of the finite state machine. And then there's the next state function, and the next state function computes what the next state inside of the finite state machine is going to be based on the current state as well as the input. Now, why are we talking about finite state machines? So finite state machines are used in computer architecture for building all kinds of controllers that orchestrate what the CPU does. Okay, they're usually used for building controllers, and usually these controllers are aware of, what did the CPU previously do and what it needs to do next, and that's why they need some kind of state. So we're going to look at finite state machines abstractly today, and we're going to do an example of how to use a finite state machine, not in a kind of a CPU, but in a different setting. And later on in the course, we might revisit finite state machines and how we use them to build controllers. Okay? So kind of a brief illustration of what I just mentioned. A finite state machine has an input. So if this gray logic block represents the logic block for the finite state machine has an input, it has an output, and it has an internal state. And the output is going to be computed as a function of the state and the input, and this is the output function. So I'm going to have some combination logic here that computes the output as a combination of the input and the current state. And then I'm also going to have a next state function that reads the current state and the input and computes the next state. And this next state is going to come back and be provided as an input to the state element, so that on the next active edge, the state element will update its value from the current state to the next state. Okay, so this is what a finite state machine is abstractly, and I'm about to do an example to make this kind of more clear. But does anybody have any questions so far before I move on? Okay, let me move on to the example then. Before the example, I just want to point out that in this class, we're going to focus on finite state machines where the output only depends on the current state. Okay, so in this class, we're going to look at finite state machines where the output only depends on the current state. The output is going to be independent of the input. Okay. All right, so let's do an example. The example we're going to do is we're going to build a finite state machine that controls a traffic signal at an intersection. So we have an intersection. There's two roads that intersect, and we usually have traffic lights that turn red or green to allow cars to pass. And there's usually a finite state machine that's used to control these traffic lights. And what we're going to do is we're going to build a finite state machine to do that. Now, the finite state machine is going to take two inputs, NS car and EW car. And what these inputs are, our NS car is going to tell us that there is a car waiting on the north-south road. So we're going to have sensors with our traffic lights, and these sensors are going to sense whether there's a car on the road or not, waiting to pass. So NS car will tell us that there is a car waiting to pass on the NS north-south road, and EW car tells us that there's a car on the east-west road. So these are the inputs, and the outputs are going to be commands to the traffic lights to turn green. So NS light is going to be 1 if we want to turn the north-south light green. It's going to be 0 if we want to turn the light red. And then EW light is going to be 1 if we want to turn the east-west light green. Otherwise, we're going to turn the east-west light red. Okay. Now I've made a lot of simplifications here. Usually these controllers are a little bit more complicated. There's the yellow light, and there's usually a pause in between the different things that happen. But here we're just going to have a simplification where either north-south light is going to be green and east-west is going to be red, or the opposite. North-south will be red and east-west will be green. So any questions about the inputs and the outputs? Okay. Next, I'm going to describe what the rules are for this finite state machine, for the traffic lights. So the rules are going to be as follows. Rule number 1 says that if a car is present on one road, but not the other road, we're going to turn green on the road where the car is. Okay, so if I have a car on north-south, but not a car, but there's no car at east-west, we're going to turn north-south 1 and east-west 0. Similarly, if I have a car on east-west, but no car on north-south, then we're going to turn on east-west, and we're going to turn off north-south. Okay, by off I mean it's going to turn red. Rule number 2 says if there's not a car on either roads, then we're going to stay green on the road that is currently green. So if I don't have a car on either roads, both north-south car and east-west car are 0, then what I'm going to do is I'm just going to stay green on the road that I was green on before. So if I was green on north-south before, I'm going to stay green on north-south. If I was green on east-west before, I'm going to stay green on east-west. Okay? And then finally, the third rule says that if I have a car on both roads, right? So there are cars on both roads, we're going to turn green on the road that is not currently green. Okay, so if I have a car on both roads and I'm currently green on north-south, then on the next clock cycle, I'm going to switch to east-west. And if I have a car on both roads and I'm currently green on east-west, on the next clock cycle, I'm going to turn green on north-south. And this ensures that I kind of give a fair amount of time to both roads, and I constantly alternate between the different roads so that all the cars get their chance to pass. Okay, so these are the specifications for our finite state machines. Any questions about these specifications before we see how to implement them? Okay, then let's move on to see how to implement the finite state machine. So one convenient way of representing the behavior of a finite state machine is using something called a state diagram. So what we're going to do is we're first going to determine how many different states our state machine could possibly be in. So in our case over here, there are 2 possible states that the finite state machine can be in. And I'm going to call these 2 states NS green and EW green. What these states tell me is NS green tells me that the north-south lights is green, and EW green tells me that the east-west light is going to be green. Okay, so the first step is going to be to determine how many states we have. In our case, we have 2. The state diagram could the number of states could be arbitrarily large. We could have many states, but for simplicity in today's lecture, I'm just going to have 2 states in our state machine. The next thing we need to do is we're going to determine the outputs. And remember that we said in this course, we're going to focus on state machines where the output depends only on the current state. It does not depend on the input. And what that means is that for each one of these states, we have a well-defined output. So in the case of NS green, if I'm in the NS green state, this is going to mean that the north-south light is going to be green, so it's going to be 1, and the east-west light is going to be red, so it's going to be 0, right? So for in the NS green state, I'm going to write the output here inside of my inside of the circle that's representing the state, because the output depends only on the state. So here in NS green, NS light is 1 and EW light is 0. And then similarly, for east-west green state, for the east-west green state, the east-west light is going to be 1, and the NS and the north-south light is going to be 0. So the next step was to determine the outputs at each one of these states. Okay? Any questions so far? Okay. Well, now that I've determined how many states I have, and I've determined the outputs for each one of these states, the next step is to determine how I'm going to transition between these different states. And to determine how I'm going to transition between these different states, obviously this is going to depend on the input that I have. What I'm going to do is I'm going to go back to the rules that we stated before, and I'm going to convert those rules into transitions in my state diagram. Okay, so let's start with rule number 1. So rule number 1 tells us that if a car is present on one road but not the other road, we're going to turn green on the road where the car is. Okay, so let's start with the case where the car is present on the north-south road. So here the north, let's say that NS car is 1 and EW car is 0. So I have a car on the north-south road and I don't have a car on the east-west road. So let's say I was in the north-south, in the NS green state, right? So I was green on the north-south road, and then I get the input, NS car is 1 and EW car is 0. What state do I go to? Do I stay in this state or do I move to this state based on this rule?
You stay.
Right, I stay exactly because we said that if a car is present on one road but not the other, we turn green on that road. So if I'm in NS green and then I got a car in north-south but no car in east-west, I'm just going to stay in NS green. And that's what happens. If my input is 1, 0, and I'm in NS green, I'm going to stay in NS green. Okay. What if I am in EW green? So if I'm in EW green, and then I get NS car is 1 and EW car is 0. What do I do? Right, I'm going to transition to NS green. So, and then the way I represent that is I'm going to have an arrow from EW green to NS green. And notice how I'm putting the input configurations on these arrows, because this arrow represents that I have a current state and then I have a next state based on this input. So this arrow is saying that when my current state is EW green and my input is 1, 0, my next state is going to be NS green. Okay. And now let's look at the other case that also applies to this rule. So when north-south car is 0 and east-west car is 1, so I have this car on the east-west road but not on the north-south road, and I'm in the NS green state, what am I going to do? If my input is 0, 1 and I'm in NS green, what do I do? Right, I'm going to change to east-west green, exactly. And then if I'm in the EW green state, and I get 0, 1 as an input, so I get a car on the east-west road, but not on the north-south road, what do I do? Right, I stay, exactly. So I'm going to stay, I'm going to transition and stay on this state over here. And this is when NS car is 0 and EW car is 1. All right, great. So now what we've done is we've applied rule number 1. Now let's go and apply rule number 2. So rule number 2 tells us that if a car is not present on either roads, I'm going to stay green on the road that is currently green. So if my input is 0, 0, right, I'm going to stay green on the input on the case where it's where I'm going to stay green on the light that was previously green. So if I'm in NS green and I get 0, 0 as input, what am I going to do? Right, I'm going to stay on NS green. So here, for this transition over here, this transition happens in two cases: when NS car is when we have our inputs are 1, 0, and also when our inputs are 0, 0. Okay. What about EW green? If I have EW green and I get as input 0, 0, what do I do? Right, I'm going to stay, exactly. So here I'm going to stay I'm going to have ns car equals 0 and EW car equals 0. I will stay on this state. Okay. Now we have one more rule, and that's the third rule. The third rule tells us that if a car is present on both roads, we're going to turn green on the road that is not currently green. Okay, and this ensures that both roads have a fair amount of time on the green light. Okay, so here if I'm in NS green and I get 1, 1 as an input, I have cars on both sides. What do? I'm going to change exactly. So here, if I get NS car, if I get 1, 1, I'm going to follow this arrow here and change to EW green. And if I'm in EW green and I get 1, 1, what do? Right, I also transition. So here, NS car equals 1, 1 corresponds to this transition over here. Okay, and with that, what I've done is I've built a state diagram, and the state diagram tells me how many states I have. For each of these states, what the output is going to be, and for every possible combination of the input, so for each state, for every possible combination of the input, what transition I should make. Okay, so in other words, for each current state and for every possible combination of the input, what should be my next state? Okay, any questions?
طب everything depends on the inputs. How كيف كنت عم تقول إنه it doesn't depend on the input?
No, what I said is the output does not depend on the input. So here the output is only going to depend on the current state. It's not going to depend on what the input is. So here NS, if I'm in the NS green state, the NS light is going to be 1, EW light is going to be 0, regardless what inputs I have. The input is only going to affect the next state. The input affects what state I go to at the end of the clock cycle on the active edge. It does not affect what the output itself is going to be.
Oh,
Is that clear?
Thank you.
Yep, you're welcome. Okay, so now before I implement a circuit that fulfills this state diagram, what I'm going to do is I'm going to assign a binary value to each state. So in this case, I have 2 states. So how many bits do I need to represent 2 states? Right, this is simple, guys. If I have 2 values I want to represent, how many bits do I need to represent them? If I have 2 values I want to represent, I need 1 bit to represent them, right? Because if I have 1 bit, it's either going to be 0 or 1. So 1 bit gives me 2 values. So in order to represent, we need 1 bit to represent 2 states. In general, if we have n states, we need the ceiling of log 2n bits to represent them. So if I have 3 or 4 states, I'm going to need 2 bits. If I have 5, 6, 7, or 8 states, I'm going to need 3 bits, etc. Okay? But to keep this example simple, we picked an example that just has 2 states and therefore only needs 1 bit to represent it. Okay? So what I'm going to do is I'm going to assign the value 0 to NS green and the value 1 to EW green. So I'm going to have 1 state bit, and if that state bit is 0, it means my state is NS green. If that state bit is 1, it means my state is EW green. Now, I could have done it the other way. I could have assigned 1 to NS green and 0 to EW green, and this would have changed my implementation a little bit, but the overall specification functionality would have been the same. Okay, so these are the bits that I assigned to my states. Now that I've kind of assigned bits to my states, to my outputs, to my inputs, let's go and implement this finite state machine. So remember, I said before that the finite state machine has 2 different sets of combination logic. One of them is the output function, and the other is going to be the next state function. So let's first look at the output function. So the inputs to the output function are simply the current state, and then the outputs are obviously the outputs. So the output of the output function is the outputs. So here I'm going to draw a truth table that has the current state and the outputs. And this truth table is going to represent my output function. And here what I'm saying is that if my current state is 0, then ns light is 1 and EW light is 0. So here if my current state is 0, then ns light is 1 and EW light is 0. Similarly, if my current state is 1, then ns light is 0 and EW light is 1. So here if my current state is 1, then north-south light is 0 and east-west light is 1. Okay? Any questions on how I got this truth table for the output function from the state diagram? Is that clear to everyone?
Professor,
Yes?
we set NS green to be 0 and EW green to be 1, and can we change that? It doesn't matter which one is one. Which.
Yes, you can. So as I mentioned previously, we could have made NS green 1 and EW green 0. Okay, and that would have kind of changed the values here in my truth table, but ultimately I would have got the same functionality. So both ways are correct. Okay, so someone's asking about the truth table. So what I want to do is I wanna extract a truth table for my output function. My output function represents my outputs in terms of the current state. So here, when the current state is 0, the output's going to be 1, 0. So here, what I did is I filled a row for this state. When my current state is 0, my outputs are 1, 0. And then when my current state is 1, my outputs are 0, 1. So this is going to be another row in my truth table. When my current state is 1, my output is going to be 0, 1. Okay, is it clear now? So the output function we said depends only on the current state for the state machines that we are looking at in this course. Okay, so no, the output is not going to depend on the input. It's only going to depend on the current state. But as you will see shortly, the next state function is going to depend on both the current state and the input. And actually, let's jump and do that so things become a little more clear. So for my next state function, the next state function is going to compute the next state based on the current state as well as the inputs. So what I'm going to do is I'm going to extract a truth table for my next state function. So here the inputs to my next state function are going to be the current state as well as the two inputs to the logic block, ns car and EW car. And the output of my next state function is going to be state next, my next state. Now let's see how I am going to fill out this truth table. I'm going to have all combinations, the three inputs, the current state and the NS car and EW car. I'm going to have all combinations of these. Okay. Now when now the question is, what is going to be my next state when my current state is 0 and my inputs are 0, 0? Well, I simply go and look at my state diagram. So when my current state is 0, 0, well, that corresponds to this state over here, right? And when my input is 0, 0, well, this corresponds, what is the transition out of the state that has 0, 0? Well, this corresponds to the transition over here. Here, my input is 0, 0. Well, in this case, what's my next state going to be? Well, my next state is going to be NS green. So my next state is going to be 0. So here I'm going to put 0 as state next. Okay, let's do another example. If my current state is 0 and my input is 0, 1, right? So this my current state is 0 corresponds to NS green, and my inputs being 0, 1 corresponds to this case over here where NS car is 0 and EW car is 1. So when my current state is 0 and my input is 0, 1, I'm going to follow this transition. So my next state is going to be 1. So here for this output of the truth table, I'm going to put 1. Okay, I'll do one more example. If my current state is 1 and my input is 1, 0, I want to find out what my output is going to be. So here, if my current state is 1, that's this state over here, and my input is 1, 0. So where does 1, 0 take me from here? Well, 1, 0 is right here. This is the transition that has 1, 0. So if in this case, I will follow this transition. So my next state is going to be 0. And that is how I find out that this next state value here should be 0. Okay? Is that clear to everyone how I got these two truth tables? Any questions?
Doctor,
Yes?
there's something I couldn't get. How it doesn't depend on the rule. And for the first case, okay?
You mean how come the output doesn't depend on the input?
On the rule مثلا بالكيس تاعت 0 0 الرول كانت إنه we don't change it if they are both 0 0.
Can you be clear? Can you be a little bit more clear where you're referring to? Are you referring to the output function or the next state function?
To the next state.
Okay, so the next state function does depend on the input.
Oh, okay.
So here in this truth table, our inputs are the current state, north-south car, east-west car, and our output is going to be the next state. So the next state function does depend on the input. What doesn't depend on the input is my output function, which is this truth table over here. Okay?
Oh, okay.
In my output function, right, if I am in the east-west green state, so if I'm in the east-west green state, then my east-west light is going to be 1, my north-south light is going to be 0, and that's going to be the case for the entire clock cycle, regardless of what my input is going to be.
Okay, I got it.
If my input changes in the middle of the clock cycle, I'm not going to change my output. My output will only depend on my state, not my input.
Okay.
Right, and this makes sense because if I have a traffic light, I don't want to change it the minute that a car arrives. I want to kind of wait a certain amount of time and only change the light periodically so that things are a little bit more predictable. Okay.
Okay.
Yeah. Any other questions from anyone? Okay, so now that I have the truth tables for my output function and my next state function, the next step is to extract the logic equations, the simplified logic equations. Now you guys already know how to do this. You can, so this one over here is quite simple because we only have one bit as an input. So here NS light is just going to be not state current, and EW light is just going to be equal to state current. So that's going to be my output function. NS light equals not state current, and EW light equals state current. And then for my next state function, I have 3 inputs and 1 output. So I'm just going to put these. I'm going to kind of put lay out this truth table on a Carnot map. I'm going to simplify it, and then it'll give me this final result over here, where state next is equal to state current and not NS car, or not state current and EW car. Okay. So these are my output function and my next state function. Now the final step is to go and implement my finite state machine based on these equations. So let's do that. So here, this is the logic diagram for my finite state machine. These are my equations down here. I have my 2 inputs, NS car and EW car. I have my state. In this case, my state is just going to be 1 bit. So I'm just going to have 1 state element. If I have 2-bit state, I'll have 2 state elements, etc. And then here I have my output NS light and EW light. So I'll start by implementing the output function. So the output function says that NS light is just not state current and EW light is state current. So we can implement it like this. NS light is not state current and EW light is state current. Okay. And by the way, I'm showing this logically, but as you guys know, this is going to be a flip-flop. It's going to give me both the value and its inverse, so I can just get the inverted value from there. But I'm showing this inverter because I'm showing you logically what is going on. And then finally, I'm going to implement my next state function, and my next state function is going to take my current state and the inputs as an input. So here I'm going to, and it's going to implement this equation. So here I'm going to have state current and not NS car, or not state current and EW car. and this is going to give me my next state at the output of the OR gate. I'm going to take that value and I'm going to bring it all the way back as an input to my state element, so that on the next active edge, the state element will get updated from the current state to the next state that I just computed. Okay, and this is how we can implement a controller that controls the traffic, it controls the traffic lights at an intersection based on the rules that we have specified. Anybody have any questions? Is this clear to everyone?
Yes, please. Can you repeat the next state function? How did we implement it? Not how did we implement in the circuit, how did you bring the equation?
Okay, let me go back to that slide. Do you mean how I got the truth table, or how I went from the truth table to the equation?
No, the truth table to the equation.
So I just used a cardinal map. I skipped that step intentionally because you guys already know how to do this. But you can just use a 3-variable cardinal map where my input variables are state current, NS car, and EW car, and my output is state mixed. Okay, so you didn't follow because I didn't explain that. I just skipped that step, but you guys can do that on your own as an exercise.
Okay. Okay.
Using a cardinal map. So someone's asking, where do I get NS car and EW car from? Yes, I have I have sensors on my intersection that give me a 1 if there's a car waiting on the road, and gives me a 0 if there are no cars on the road. Correct. So that's what my inputs mean.
Professor,
Yes.
can we always come up with output functions that are independent from the input? Or are there some cases that we can't?
So it depends on your specification, what you're trying to implement. Now, usually you can convert you can usually convert a finite state machine where the output depends on the input to a finite state machine where the output does not depend on the input. So there's usually a conversion that you can make, and you guys will go into these the details of finite state machines and how to implement them and how to optimize them. Sorry, the theory behind them and how to optimize them in another course, which is CMPS 257. In this course, we're specifically interested with given a finite state machine, how can we implement it in hardware? Okay, but yes, you can usually go from a finite state machine that where the output depends on the input to a finite state machine where it does not. CMPS 257 is the course where you guys will learn about finite state machines in more depth. Okay, other questions? All right, well, if there are no other questions, then that's all for today. If you would like to read more about finite state machines, you can refer to section B.10 in the textbook. And that is all. I'll see you next time.
Thank you, Professor.
Yeah, you're welcome. Bye, everyone.